your lab. Floor is yours.
Thank you for the introduction. I'll be speaking about the stability studies conducted at the Jánossy Underground Research Laboratory, and a little bit about the content that I'll be going over for this talk is the motivation behind our experiment, the research laboratory and the equipment used itself, the analysis procedure, our findings, future improvements, and the conclusion. So why study long-term radioactive decay? Radioactive decay is one of the fundamentals of nuclear physics, and in recent years it has been a trending topic because several studies have shown annual oscillations, solar correlations, and time-dependent decay rate anomalies. So these claims remain controversial because the detector systematic itself can mimic tiny effects. These are physical impacts of the instrumental conditions, environmental conditions, and even the analysis procedure. On the right, we can actually see the Jenkins and Fisbach research that shows direct correlation of decay measurements to solar X-rays. However, it is important to mention that subsequent high-precision measurements, such as the ones conducted at the Gran Sasso National Laboratory, did not confirm such modulations. And this is because the challenges that we face is that the detector and the environmental conditions have to be very stable over very long periods of time, such as months to even years. So any tiny changes in gain, dead time, background, as well as the analysis window that is chosen for the research, all can produce variations in count rates. So what we require is a very high precision detector as well as environmental control. So our research aimed to produce a stable laboratory environment that can complete these high precision measurements. So a little bit about this laboratory itself is the Jánossy Underground Research Laboratory, also known as the JUR Lab, and I'll be referring to it throughout the talk. It is conveniently an underground laboratory that allows reduced cosmic ray background, as well as a more stable environmental condition and lower long-term fluctuations for such measurement. It is located at the Hunra and Wigner Research Campus. It is 30 meters below the surface, with having 3 different levels of tunneling. Our experiment is actually conducted on the 3rd level, with currently 3 other researches going on. It is part of the low radiation background section of the Westergomi High Energy Laboratory, and it's been part of the long-term monitoring campaign from 2022 to 2024. On the plot on the bottom, we can actually see the continuous environmental monitoring going on at the research lab. We can see a 1-week-long period of temperature measurement and AC system, which runs every day starting in the morning for a few hours to flush out radon or built-up temperature. We also conduct pressure and humidity monitoring, as well as radon levels. So our experimental setup is shown on the pictures on the right. We use a high-purity germanium detector. To limit thermal noise, we actually have to cool the detector to about 77 kelvins, and this is done with the help of liquid nitrogen and a 30-liter dewar. The data acquisition is conducted through a Canberra Lynx digital signal analyzer, which allows remote control, which is great because we would like to minimize human exposure in the laboratory to not disturb any of the ongoing experiments. The only time that human input is required is whenever we're filling the dewar with liquid nitrogen. This happens to about every 10 to 12 days. And we also see on the disc over here our cesium sources placed in this plastic disc that are placed in our plastic holder covered with a couple of centimeters of lead shielding. This is actually very convenient because there are mandatory inspections for our sources, and this allows easier removal for that and also keeping the source at a specific distance from the detector. Why choose cesium as our source? That happened to be because it has a very long half-life of about 30 years, so this allows the activity to change only slowly throughout the period of our measurement and allowing a simple separation from the exponential decay trend versus the environmental or instrumental drift. It also has a strong isolated peak at 661 kiloelectron-volts. So it's very suitable for such measurement. We also measured in our background the naturally occurring potassium-40, and we used it as a stable reference because it is effectively constant over the duration of our experiment because of its long half-life of about 1.2 billion years. We can also see the plot showing our run times versus the simultaneously monitored environmental conditions. The timeline of our measurement has been the following. We conducted a 0th run that was our test run to identify calibration, radio isotope positioning, and shielding. Our runs were stopped during run 1 and run 3 for a very quick systematic interruption, as well as a signal generator connection, and one time an isotope removal inspection during run 3. That's why the drop in total counts. Other than that, the other runs ran smoothly. It is also worth mentioning that for run 2, the increased count rates is actually due to the fact that the source has been moved closer to the detector. And this also shows the sensitivity of the equipment. And every time the geometry of the source has been changed, that meant the end of a run. So the detector stability and analysis was studied with the help of peak positioning stability, gain drift, background stability, count rate consistency. And we observed cesium peak centroids, the potassium peak centroids, our peak area evolution over time, as well as their ratios. After the data has been acquisited from the detector, we energy calibrated it and lifetime corrected it, and then proceeded to peak analysis, which was done with peak extraction, background subtraction of 3 different methods, a sliding window averaging of 6 consecutive hours worth of data sets being combined. This reduced systematic fluctuations, still allowing us to see smaller drifts. And we also monitored the long-term trends with error propagation and weighted trend fitting. The peak extraction, so the background subtractions that we have used were polynomial background fitting of first order, seen in the first plot, second order, and then a SNP algorithm. For cesium on the far right over here, the different methods of background subtraction actually produced very similar results. However, for potassium, there has been a slightly larger agreement. This is due to the peak sitting at a more substantial background continuum. And a little bit about the SNP algorithm that we have used. It stands for statistics sensitive nonlinear iterative peak clipping. As the name suggests, it's an iteratively suppressing narrow peak. It produces a smooth estimate of the Compton background, and it still preserves the slowly varying continuums. And it also offers us the improved option of having to not worry about the analysis window chosen, as that can also, as mentioned earlier, impact the measured count rate. So that is also an eliminated extra that it provides. So the stability of the detector was analyzed with the help of the ratio of the cesium over the potassium. It is a useful observable because it allows us to better understand the detector response. And as we can see, it was proven to be pretty stable. So because cesium and potassium were exposed to the same environmental and instrumental conditions, it allows us to reduce detector efficiency effects, common mode gain fluctuations, and some of the environmental systematics. We also analyzed the peak centroid evolution over time. And what we have seen were small correlated centroid motion, so a tiny drift. This indicates an instrumental effect consistent with calibration drift rather than environmental or instrumental drift. It is not a big systematic drift. However, for such high precision measurements, it would still be important to monitor these better. So we would like to implement a dynamic peak tracking and more calibrations throughout the run. A little bit about the background level comparisons to see where the Jura Labs results are at is in yellow, we can actually see our Jura Lab background levels, the unshielded ones. with the dotted black lines being our baseline, compared to some of the other shallow underground laboratories. The blue line is the Felsenkeller bunker 110, and the red line is that of the Slanik-Prahova baseline. What is important to mention is that these are only qualitative comparisons because the laboratories themselves are completely different. The shielding, the detector used, and the source positioning are all varying and different. But what it does is actually allows us to see what improvements to make and how close we are to what we'd like to achieve. The Slanik-Prahova baseline is so much lower because the laboratory itself is it's conducted in a previously salt mine operated positioning laboratory, and it is 2 orders of magnitude lower than ours. However, the Felsenkeller one is a lot closer to being comparable to our laboratory. This is a bunker as well. It's similar to what our laboratory is like. And those results are actually comparable. As we can see, it is only less than 1 order of magnitude lower than our baseline. And even towards higher energies, we are actually able to produce a background that is lower than that of the Felsenkeller. Our aim is to actually implement some setup improvements that can allow us to reduce our baseline to that of these best shallow underground laboratories. So with our limitations of gain, drift, calibration, run times, length, we would like to implement improvements towards dynamic peak tracking, calibration, improved shielding, improved environmental conditioning, and have a dedicated low radiation chamber set up in our laboratory. So to conclude, we were successfully able to develop a long-term underground decay measurement setup that allowed the characterizations of background stability and define multiple peak area extraction methods and background subtraction, and produce results that are comparable to that of the best shallow underground laboratories themselves. And for future plans, we would like to have a better control of the systematics, implement some improvements to the experimental setups mentioned earlier, and implement dynamic analysis. So thank you for your attention.
So thank you for the nice presentation. Is there any question for Franciska?
Thank you, very interesting. For me, I have a naive question, so I am not familiar with all this. So going deep in Earth, it's high because you have to dig deep or find a mine, but going deep in water is easier. So are there laboratories or tests that are deep in ocean, or is it a possibility, or the shielding is so different that it is not an option?
Thank you for the question. I do not know of such laboratories. I also think it would be very difficult, and another issue with it could be pressure. That could also impact it. But I haven't heard of such. Have you?
Thanks. So first of all, I mean, water equivalence is a unit, so everything is calculated because that's an easygoing thing. So typically, underground laboratories has completely different rock structure, rock formation. So this makes so one of the most relevant in this studies are the ground sasso, which is very many meters below, like I think 2 kilometers below the top level. There exist underwater experiments. The most famous is the ice cube, which is located in the Antarctica, and they dig holes and put into ice. That's for neutrinos. I think that is also sensitive to muons because it just captures the Cherenkov light, and this is also true for that. But this specific things is typically to put a sample into the detector. So this is much better if you have a solid surface and not put do anything with the high pressure water, which can leaks to everywhere. Yeah. My question is related to the last plot you had, if you go back. So if we would apply the shields, what we are planned, that how much orders of magnitude we can gain with the lead shielding?
With that shielding itself, for example, Felsen Keller's bunker without the shielding produces this line over here, the blue one. With shielding, they actually go to as low as about over here. So our experiment as well with shielding, definitely at least 2 orders of magnitude lower and reaching that of the Slanik-Verhova baseline.
So this means that what we can get is the high energy muons and astroparticles to suppress, and then the soft
Yes.
can be with local shielding. Yeah.
Yeah.
Thank you.